Hello everyone, I'm Professor Xiaonan Gao. Welcome to a general chemistry class. This session will continue with the chapter Liquids, Solids, and Intermolecular Forces. In the last session of the general chemistry class, we'll discuss about the crystal structures. Crystals, solid structures having plane surface, sharp edges, and regular geometric shapes, have aroused interest from earliest time, whether as ice, rock salts, quartz, or gemstones. Only in relatively recent times have we come to a fundamental understanding of the crystalline states. This understanding starts with the invention of the optical microscope and was greatly expanded following the discovery of the X-rays. The key idea, now supported by the countless experiments, is that the regularity observed in crystals at the microscope level is due to the underlying regular patterns in the arrangement of atoms, ions, or molecules. So this session, we are going to fully explore what are the crystals. What are the crystals? A crystalline solid possesses rigid and long-range orders. In a crystalline solid, the atoms, molecules, or ions occupy specific, or you can say predictable positions. For amorphous solids, they don't possess a well-defined arrangement and long-range molecular orders, like glass, which is optically transparent fusion product of the inorganic material that has cooled to a rigid state without crystallization. And compared to the well-arranged order of the quartz, the amorphous glass possess chaos arrangement of the silicon dioxide in its structures, and that's why it is amorphous. Well, you can probably think a number of situations in which you have to deal with repeating patterns in one or two dimensions. Well, this might include projects like stringing beads to make a necklace, wallpapering a room, or creating a design with floor tiles. The structure of crystal, however, must be described through a three-dimensional patterns, and these patterns are outlined against a framework called a lattice, comprising the intersections of the three sets of the parallel planes. Well, lattice planes intersect to produce three-dimensional figures having 6 faces arranged in 3 sets of parallel planes. And these sets of planes are called the unit cells, which can be used to generate the entire lattice by replicating it along the 3 perpendicular directions. Where possible, we arrange the 3-dimensional space lattice so that the center of the structure particles of the crystals are situated at lattice point. And the centers can be atoms, can be molecules, and can be ions. There are generally 7 basic unit cells. Simple cubic, all the edge lengths A, B, and C are equal, and the angles in between alpha, beta, and gamma are all 90 degrees. Tetragonal unit cell has a square plane, but the C doesn't equal to A and B, and the angles in between alpha, beta, and gamma are all 90 degrees. And in orthorhombic unit cells, A, B, and C are all different, but alpha, beta, and gamma are all 90 degrees. And next, in the rhombohedral unit cell, A, B, and C, all the 3 edge lengths are equal, but the values of the alpha, beta, and gamma, they are all equal, but not as 90 degrees. Next is a monoclinic unit cell. A, B, and C are all different. Alpha and beta are 90 degrees, but gamma is another value. And for the triclinic one, A, B, and C are all different. Alpha, beta, gamma are all different, and they are not equal to 90 degrees. Last one is very interesting. That is a hexagonal unit cell. A and B are the same, but the height C is different. Alpha and beta are 90 degrees, but gamma is 120 degrees. For the simple cubic unit cell, there are 3 different subtypes. The first one is a simple cubic. Only 8 atoms sit at the corner of the unit cell. Second is a body-centered. Compared to the simple cubic, there is 1 more atom lying in the center of the cubic. And last one is a face-centered cubic. Compared to the simple cubic, there are 6 atoms on the 6 face centers of each face. In the simple cubic unit cell, do the atom only belongs to the mentioned unit cell? Actually, it is not. The atoms are lying layers by layer like this arrangement. And for each atom at the corner of the unit cell is shared by 8 unit cells. So you can only count for 1/8 of the atom for the specific unit cell. And for the body-centered unit cell, the atoms inside of the center of the cell entirely belongs to this unit cell. And the other atoms are also shared with the other unit cells. So, we talk about the corner atoms, and they are shared among 8 unit cells. So therefore, only 1/8 of each corner atom should be thought as belonging to the entirety of the given unit cell. The edge-centered atoms are shared among 4 adjoining unit cells, and only 1/4 of the edge-centered atom should be thought as belonging entirely to this given unit cell. And last one is a face-centered atom, and they are shared among 2 adjoining unit cells. So only half of the face-centered atom should be considered as belonging entirely to this given unit cell. Now let's count how many atoms are there in the 3 unit cells. For the simple cubic, there are just 8 corner atoms, so 8 times 1/8 is 1. There is just 1 atom in each simple cubic unit cell. Next, for the body-centered cubic unit cell, there are 8 corner atoms and 1 center atom. So therefore, 8 times 1/8 is 1, plus 1 equals 2. So there are 2 atoms in each body-centered cubic unit cell. And for the face-centered unit cell, there are 8 corner atoms and 6 face-centered atoms. Therefore, 8 times 1/8 plus 6 times half is 3. And 1 plus 3, the total is then 4. So there are 4 atoms in each face-centered cubic unit cell. Well, if the radius of an atom is r, then how can we calculate the edge length of the unit cell? Let's see here. For the first one, the simple cubic, just add the 2 radius together, and you'll get the edge length of 2r. And for the body center, it's a little bit complicated. The edge length, a squared plus a squared plus a squared equals 4r squared. 1r from the corner atom, 2r from the body center, and 1r from the corner atom. So 4r together. And overall, that is 3a squared equals 4r squared. And the edge length, a equals 4r over the square root of 3. And for the face center one, well, the edge length, a squared plus a squared equals 4r squared here. Therefore, the edge length a equals square root of 8 times r. Unlike boxes, which can be stacked to fill all spaces, when the spheres are stacked together, there must be some unfilled spaces. In some arrangement, however, the spheres come into a close contact as possible, and the volume of the holes or walls is a minimum. These arrangements are known as closed packed structures and are the basis of a number of crystal structures. To analyze the closed packed structures, imagine one layer of the sphere, layer A, the blue color, in which each sphere is contacted with 6 others arranged in a hexagonal fashion around it. Among the spheres, there are holes. And the holes between the 3 spheres resembling a triangle is called a trigonal hole. Once the first layer is placed in the next layer, the layer B, the brown color, the entire pattern of this layer is fixed. Again, there are holes in layer B as well. But the holes are of 2 different types. Tetrahedral holes fall directly over the sphere in layer A, and the octahedral hole that falls directly over the holes in layer A. So there are 2 possibilities for layer C, the third layer. In one arrangement called hexagonal closed packing, HCP, all the tetrahedral holes are covered. So layer C is identical to layer A, marked as blue color here again. And the structure begins to repeat itself, A, B, A, B. And in the other arrangement, called the cubic closed packing, all the octahedral holes are covered. And the sphere in layer C, the green color, are out of the line with those in layer A. So only the 4th layer is added that the structure begins to repeat itself. In the explored view of the 2 packings, well, the hexagonal closed packing has a A, B, A style, while the cubic closed packing has a A, B, C, A style. Now, I have introduced a lot about the crystal structures already, but how can we define the structures? For crystal structure determination, X-ray diffraction is a very powerful tool. When the X-ray passes the slate and hits the crystal, it can get diffracted, and then hit the detectors to give the signal. And according to the signal, we will be able to find the lattice space. Specifically, 2 rays in a monochromatic X-ray beam, which gives single wavelength X-ray labeled A and B, and wave A is diffracted or scattered by one plane of the atom or ions in a crystal, and wave B from the next plane below. And wave B travels greater distance here, and the extra distance equals BC plus CD. And BC plus CD equals 2D sin theta. And the intensity of the scattered radiation will be greatest if the wave A and B reinforce each other. That is, if their crest and choke line up. To satisfy this requirement, the additional distance traveled by the wave B must be an integral multiply of the wavelength of the X-rays. Therefore, n lambda equals 2D sin theta. From the measured angle yielding the maximum intensity of the scattered X-rays, the X-ray wavelength lambda, we can calculate the spacing between the atomic planes. With different orientations of the crystal, we can determine the atomic spacing and the electron density for different directions through the crystal. In short, the crystal structures. So far, there are mainly 4 different types of crystal in the world: ionic crystal, covalent crystal, molecular crystal, and metallic crystal. The first one is the most common crystals, ionic crystal. For ionic crystal, the lattice point occupied by the cations and ions and held together by the electrostatic attractions. The crystal structures make them hard, brittle, and high melting point. However, since the ions are in fixed positions, they also possess poor conductivity of the heat and electricity. These 3 ionic compounds, cesium chloride, zinc sulfide, and calcium fluoride owns 3 typical ionic structures, which you will learn in your advanced inorganic chemistry course. Next category is a covalent crystals. Their lattice points are occupied by atoms, while covalent bonds. And the covalent crystals possess hardness and also high melting point. And covalent crystals are also poor conductors of the heat and electricity as well. Diamonds and graphite are common covalent crystals examples formed by the carbon atoms. Next is molecular crystals, and the lattice points are occupied by the molecules, while intermolecular forces. And the molecular crystals are usually soft with low melting points, and they are also poor conductors of the heat and electricity as well. Ice is a typical molecular crystals, and freezing benzene as well. Inside of the ice and benzene, they are connected while the intermolecular forces, so they are easy to melt inside of the solvent. Last category is metallic crystals. Their lattice points are occupied by metal atoms, and they are held together by metallic bonds. Well, for the metallic crystals, they vary from soft to hard, and also from low to high melting points. Although the metal atoms are in fixed position, like this way, their electrons can move freely inside of the crystals, called as a mobile sea of electrons. Therefore, metallic crystals are good conductors of heat and electricity. This table lists the characteristics and properties of the 4 crystals. Please spend time after class to memorize these contents, which will help you to better understand their similarities and also difference. Alright everyone, in this session we learned about the crystal structures. I hope you have enjoyed the whole general chemistry class and wish you have a great success in the future. Alright everyone, in this session we learned about the crystal structures, and I hope you have enjoyed the whole general chemistry class and wish you a great success in the future. Bye.